this is that. Today we now be doing question 3 of 2015. Whoa, now we got approximations. And so we learned this topic which deals with this kind of stuff. It's called Taylor series. What are Taylor series? It's basically approximating functions with polynomials, and this is exactly what we are gonna do here. So, give an example on two functions f and g such that f is a good approximation G, but f is not excellent approximation G. There can be many others, but the first thing that comes to mind are x and x plus 1 over 200. Wow. So, on the remainder of the question, show that if this, then f is an excellent approximation to G. So we're going to find the maximum of sine 4x squared over 400. So dx equals to 8x sine 4x squared over 400. Great. So now we're going to find a maximum. So dx equals to 0. Either x equals to 0 or sine 4x squared equals to 0. So this means that 4x squared equals to pi over 2, and therefore this means x equals to the square root of pi over 8. And so this means that we are now going to calculate square root of pi over 8. So square root of pi over 8. So the maximum error in this case is 1 over 400, which, and you ask me, it's not very much. And in fact, it's less than 1 over 320. Besides, who makes these bounds? They're arbitrary. Now we're gonna use the exponential function. Just kidding, we're gonna use the definition on the exponential function. So f of x, so g of x equals to 1 plus x, we're going to integrate this term by term, plus x squared over 2 plus x cubed over 6 plus x4 over 24. Now when you continue integrating this and adding 1, you will get a series which is known as the exponential series. So it's a Taylor series for the exponential function. So we are now going to calculate the error. So we need to find this maximum. Since x over 24 doesn't have a maximum, we need to calculate half 4 over 24, which is 1 over 384. Again, who makes these bounds? So you are given that h of x minus f of x has a maximum value. Explain why. This. Because x4 over 24 does not have a maximum. It just has a local minimum x equals to 0. However, the maximum on this integral is when x equals to half. Therefore, x dot is 1 over 384. Done. You are also given that fx is less than hx. So that x is a good approximation to x with 0 h when 0x half. There. So since hx equals to hx is approximately equal to f of x, and then the error term is 1 over 320, and since 1 over 384 less than 1 over 100, again, who makes these bounds? Well, answer to that right away, the MAT. So anyways, h of x is f of x plus 1 over 384, give or take, and so this means h of x is a good approximation to f, and the converse applies. F is a good approximation to h. And we're done with the question. Now let's talk a bit about Taylor series. Why am I so excited about this question? Because one of my favorite Taylor series, and I was a kid, I discovered this when I was 8. So 1 over 1 minus 1 over 2 plus 1 over 3 minus dot 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 equals to one of my favorite constants of all time, ln 2. And this Taylor series also amounts to ln 2, 1 over 1 times 2, 1, plus 1 over 2 times 2, 2, plus dot 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 equals to ln 2. And then, since I love Taylor series so much, I decided to derive a huge lot of Taylor series, including this beast. It's gonna take a long one to write. You might wonder, why do I memorize this? It's because I have a lot of time on my hands and I love the magical constant ln 2. And since then, I've already computed 4096 hexadecimal digits. Okay, so we are now going to continue writing this Taylor series where I tell you more about it. So Taylor series are polynomial approximations to separate functions, and then other Taylor series for a certain number of mathematical constants can be obtained by A, multiplying by a constant, or B, changing the parameters in it. So here's the Taylor series, and you might think all of the terms are on the same form. Wanna know why? Because if you substitute and you take off all the constants, this will become ln 60 on 63, then ln 81 on 80, and so each of these little n times a to the power of n series will form some super particular ratios. And I'll post the value of this constant in the description. So, see you